And I will show you later what we can do there. So my overview is here. I will give short general information about the code, talk about the computer science aspects, computational engineering aspects. I list few applications we solved with this code, and I will finish with the conclusion and outlook. So for the general information, here you can see the code's logo, and the coloring is done with a simulation out of this code. So we were using this NML, and we're using a mesh and simulations. So the code is fully open source. It's published with the Boost license. It's available on GitHub. We have an intense documentation of the code with a lot of examples. And we have a Docker image for testing the code. So you do not have to compile the code. You can just download this Docker image, run all the examples, change the examples, and play around with the code. So the entry level is really easy. And one other thing of this code is we try to use modern C++. So this code uses the latest features provided by the C++ 17 standard. And right now we have experimental feature of the C++ 20 standard available in few of the compilers. So we are trying to add some new features to make the code more efficient and more usable. And here you can see two references. The first reference here is more about the computer science aspects of the code. And the second one is an overview of the code. It's published in the Journal of Open Source Software. And here you can find a lot of information. And then you can dig deeper into the paper we provided here. And I provided you with all of the links of the code. So for the computer science aspects, we are using HPX. And this is an open source C++ standard library for concurrency and parallelism. So what is really interesting here, HPX exposes a uniform standard-oriented API for ease of programming parallel and distributed computations. So normally you have to use MPI for the distributed part, you have to use CUDA or OpenMP for the local part on one node, and you have different APIs, different dialects and everything, and HPX unifies this with some abstraction level. So this is really easy to extend the code, and HPX provides a unified syntax. And so if you do something on a single node, or if you implement something distributed, you as the programmer or user do not see the difference here because this is all hidden by an abstraction layer in HPX. And this makes it quite easy to extend this code because you can write your serial version and run everything later, easily shared memory on a single node. And then you just have to do a few changes in the code and you can run everything we're running on one node on thousands of nodes, and you do not have to handle this MPI and all these tools. And we also have a really flexible performance counter framework, which I will show you later. And again, here we have a paper in the Journal of Open Source Software, where we have a brief overview of HPX and a lot of references if you're interested in some of the topics there. And here, this is a really nice example. It's not done with our code, but this was done with an astrophysics code we have with HPX. And normally people use MPI for communication, and MPI is synchronous, so you have to wait. And we were using libfabric, which provides some asynchronous communication. And here you can see we could scale from a single node up to 2,400 nodes using 64,000 cores on a large computer in Europe. But this is not really interesting. MPI codes can this do as well, because here we were using MPI for synchronous and libfabric for asynchronous computation. But here you can see, if you look at the figure 3, we can see that the benefit of using this asynchronous communication comes in. If you use more than 8 nodes, the code gets faster and faster. And for really large simulation, we were able to be 3 times faster than MPI, which means by just using a different communication layer with HPX, your simulation is 3 times faster. So if it's taking 3 days with MPI, you can do it in 1 day with using this different communication layer. And this is really promising for an computational expensive method like peridynamic. And another thing is load balancing for distributed non-local models, because if thing breaks and the neighborhood gets smaller, we have less computational load. And so we had a Google Summer of Code student last summer, and I mentored him with Prashant. And he was developing load balancing. So you can provide a mesh or you can provide a particle cloud. And then we do mesh partitioning with Metis. And then every few simulation step, we check if all of the processors have enough work. And if not, we redistribute our domain that each of the processors and nodes has a lot, or has the same amount of node. So this gives an additional speed up. And we have done this for non-local diffusion. We have to implement it for peridynamics because the undergraduate student, we were thinking it's easier to do the non-local diffusion, but it's really working well. And you can read the papers there for more details. So this is all about the computer science aspects. And I hope I could highlight why we wanted to use HPX for this code and not MPI and as the other tool we had used before. And here, the softening model, we have a bond-based, I showed you on the first slide. Here we have a state-based version of the softening model. And due to this softening, we could do a lot of numerical analysis with this model and could prove some really interesting things. And here's the reference of the model. And yeah, I can provide you with much more papers of Lipton groups about this. But this is really interesting to have this model because somehow, if you look at quasi-static simulations, and in our review paper, we could show that there are not many three-dimensional or at least quasi-static peridynamic simulation, because if you go from dynamic to quasi-static, it's getting much, much more expensive, even for the two-dimensional case. And this is mostly done because if you elevate the entries of the tangent stiffness matrix, you have to do the numerical derivation. And this is really expensive to do in a computational sense on your computer. And using this model here, where we have the softening, we can compute the second derivation and we can use Taylor series. And here you see again the entries of the stiffness matrix. And here you can see if we compute this K values, we have an explicit definition. So here we have to compute the sum of this Aij or Aik tensor. And here you can see we have a second order tensor. And this is really easy because you do not have to do the numerical derivation. This is really complicated. You just have to do an additional sum over the neighborhood, like computing a force you would normally do, but with a different kind of a tensor here. And then you can compute easily the entries of the stiffness matrix. And this makes the computation much, much faster. And I do not have time, but we had done some comparison with the paradigm numerical model where we compute the numerical differentiations here and got a really good speed up in this case, but I can discuss later this in the breakout room. And another thing we started to do, because peridynamic is expensive, as I told before, and so in some parts we only want to compute peridynamics where we have crack and fractures, and far away of the domain where we have the linear elasticity, we do not want to have peridynamics. We want to have something like finite elements or partition of unity methods, these local models, which are much less expensive. And what we are trying here is we're trying to couple our code with the partition of unity method code from the group of Alex Schweitzer at University of Bonn. And here you can see we solve a global problem using the partition of unity method. And then if we find some high strain or stresses, we identify a region where we want to run a local peridynamic simulation, and then we change boundary conditions to the local problem. We do a peridynamic iteration or many of peridynamic iterations. Then we extract the crack path, and then the peridynamic simulation with our code is giving back the crack path to the partition of unity method. And they use this crack path to compute enrichment functions, provide enrichment functions, and then try to do few more crack steps. And so this is a really interesting process, what we are doing with our code. And we are working that you can really run both of the codes concurrently. And then this is really automated. So this is a really nice feature we have and we are working on. And we have currently the first proof of concept. We have to do a lot of more things, but it's a multiple part series paper. But we published we submitted the proof of concept in some journal, and this is part 1. And if you're interested, you can read this preprint, and this is still under revision. Okay, for the applications here, we were using this complex fracture nucleation and evolution with non-local elastodynamics. We have free damage propagation with memory, and we have this kinetic relations of local energy balance for LFM from a non-local peridynamic model. This is shown for the bond-based, and the state-based is still under work of the group of Professor Lipton. And so I would like to come to my conclusion and outlook. So we have shown that there are some benefits from other codes using this asynchronous many task systems and not using MPI, synchronous communication, using libfabric's asynchronous computation to speed up the code easily. We implemented the softening model. We have shown a lot of these things proved in theory with our code and have done the numerical validation. And the outlook here is we want to improve the distributed implementation, because currently we only have a non-local diffusion in distributed. So we want to add all the peridynamic models we have. We have C2 bond-based and state-based softening model. We have the PMB model. We have Stilling's original state-based model implemented. And we want to add the explicit stiffness matrix in state-based. We only have the bond-based version in preparation. And we work more on the automation of the coupling with the partition of unity method. And yeah, I would like to close my talk. Thanks for your attention, and I'm happy to take questions.